All right, so now that we've categorized isolated singularities, I want to do a few examples. And so I want to show you how Lorentz series and isolated singularities kind of fit together. And so the first thing I want to do is I want to consider the function f, which would be cosine of z minus 1 over z to the fourth. And I want to think about what happens at 0. And so what we need to do is we need to compute the Taylor series for cosine. That'll lead to a Lorentz series for f. And we'll see how this works. So cosine we know is the sum from -1. So n equals 0 to infinity, -1 to the n, z to the 2n over the quantity 2n factorial. And that's cosine of z. We're going to subtract 1. 1 is what we get when n is 0. So this is basically just the sum starting at n equals 1. And so that's going to be, so at n equals 1, we're going to have negative z squared over 2 factorial, which is just 2, plus z to the fourth over 4 factorial, 24, and so on. And so when we divide through by z to the fourth, this is going to be equal to -1/2 times 1 over z squared, plus 1 over 24, 1 over 4 factorial, minus z squared over 6 factorial, which is 720, and so on. Okay, and so that's what we get. This means that 0 is a pole of order 2. And the reason why it's of order 2 is that 2 is the largest power of z that we have in the denominator. Okay, and it's z because we're looking at z minus 0 to the k. So the largest power there that we have is 2. Okay, so that's a pole of order 2. So there's one example. Next, let's look at the function e to the z minus 1 minus z over z cubed. So this is going to be very similar. The Taylor series for e to the z will lead to a Lorentz series for f. And so this is going to be, let's see, we'll have e to the z. Yeah, e to the z, let's just jump right in. E to the z is 1 plus z squared over 2 plus z cubed over 6, and so on. And then we're going to subtract 1 and subtract z. So that'll be the z squared over 2 plus z cubed over 6, and so on. Then we divide by z cubed, and then this is going to be 1/2 times 1 over z plus 1 over 6 factorial plus 1 over 24z plus 1 over 120 z squared, and so on. Okay, and so that is the Lorentz series there. So that means that 0 is a simple pole. And actually, in this case, we can say, we could have said this in the previous one as well, but we can compute the residue. So the residue of f at 0, in our case, the residue is 1/2. Let's go back real quick and talk about the previous example in the residue. Remember that the residue is the coefficient of the b1. So it's the that coefficient b1 here. And so in other words, we're looking at, you can think of this as kind of having a plus 0 times 1 over z term there. Okay, and that 0 is the residue. So the residue of f at 0 is 0. Okay, because the 1 over z term is not there, so the coefficient is 0. Here, the 1 over z term is there, and the coefficient is 1/2, so the residue is 1/2. Okay, so that's really all we need to do. There. And then let's do one more. So let's look at the function f, which is z to the fourth times e to the 1 over z. E to the 1 over z we talked about already, but this is going to be z to the fourth times 1 plus 1 over z plus 1 over 2z squared plus 1 over 6z cubed, 4z to the fourth, and so on. Let me actually just add one more term in there. So plus, not 4, but 24, plus 1 over 120 z to the fifth, and so on. And so it turns out that this is going to be, let's see, z to the fourth plus z cubed plus 1/2 z squared plus 1/6 z plus 1 over 24 plus 1 over 120 z plus 1, it would be 1 over 720 z squared, and so on. Okay, and now it turns out that all of the terms going forward will have a z in the denominator, and in particular, this means that z equals 0 is an essential singularity. Okay, so that's that's an essential singularity. Moreover, the residue of f at 0 is going to be the coefficient of the 1 over z term, so that's going to be 1 over 120. Okay, and so that's the residue of f at 0.